Welcome to this ultimate rapid-fire explainer. I'm your host, and today I'm stepping into the role of your elite academic tutor. Look, we have one goal and one goal only right now, to maximize your score on the BSNL 2026 Senior Executive Trainee Exam. The technical syllabus is absolutely vast, I know, but today we are stripping away all the fluff. We are focusing exclusively on the highest yield data from the basic telecommunications concepts section. So grab your notes, lock in your focus, and let's get to work. Okay, let's dive right in. Here is your strategic battle plan for conquering this material. We're covering the exam blueprint, signal processing, essential AM, FM, and PM formulas, pulse modulation, and finally, those high-yield exam traps.
Right, before we even touch a single equation, we need to understand the battlefield. Let's look at the BSNL exam blueprint.
This specific section accounts for a massive 15% of your technical paper, which is 160 questions total. But here's the harsh reality of this exam: a 1/4 negative marking penalty applies. Every single formula we cover today has to be memorized perfectly. The biggest trip-up zone here is simple, but totally deadly. Do not guess blindly. You either know the math or you lose the points. There's really no in between.
With the stakes set, let's shift gears into signal processing fundamentals. These are the absolute basics you need to master. So, comparing analog and digital signal processing. Analog is all about continuous time signals using hardware, things like op-amps and resistors. Digital, on the other hand, works on discrete time signals using ADCs, DACs, and microprocessors. Now, listen closely to this, because examiners love to trick you here. Do not equate DSP merely with standard computer processors. The high-yield answer they're actively looking for on this exam is FPGAs, Field Programmable Gate Arrays. Lock that acronym into your memory for sure.
Why do we even bother with modulation in the first place? Well, the core concept is translating a baseband signal to a passband signal. The absolutely crucial formula you need is that antenna height, h, equals lambda over 4, which translates to the speed of light, c, divided by the frequency times 4. To put that into perspective, if you tried to transmit a raw 15 kilohertz audio signal without any modulation, you would literally need an antenna 5 kilometers tall. It's like building a skyscraper just to make a phone call. And that brilliantly illustrates why we modulate: to reduce antenna size to something physically possible, and of course, to enable multiplexing. The trap? Forgetting that without modulation, sending multiple signals over the same medium is practically impossible.
All right, have your pens ready as we crack open our high-yield vault for amplitude modulation, or AM.
These 4 formulas are guaranteed points, guys. The modulation index, mu, is just the amplitude of the message over the amplitude of the carrier. Bandwidth is simply 2 times your modulating frequency. Total power equals carrier power times 1 plus mu squared over 2. And efficiency? That's mu squared over 2 plus mu squared. But wait, here is a classic exam trap. Even at 100% modulation, where mu equals 1, your maximum efficiency tops out at only 33.3%. Think about that. That means a massive 66.7% of your total power is completely wasted transmitting the carrier wave, which contains 0 actual information. Crazy, right?
Actually, scratch that. The exam won't always give you those standard clean amplitudes. Often they'll give you maximum and minimum voltages from a wave envelope. When that happens, step 1, pull Amax and Amin from the data. Step 2, calculate mu as Amax minus Amin, all divided by Amax plus Amin. The crucial point here is choosing the right tool for the job. Do not try to force the basic AM over AC formula if they hand you envelope voltages. It just won't work. Okay, smoothly moving away from varying amplitude, let's jump into angle modulation, specifically FM and PM.
For FM, your frequency varies linearly with the message signal. Your modulating index here is beta, which equals frequency deviation divided by modulating frequency. But remember, frequency deviation is the frequency sensitivity constant multiplied by the message amplitude. Then you've got Carson's rule for bandwidth, 2 times the sum of the modulating frequency and frequency deviation. Now pay attention to the major trip up here. Beta depends heavily on the amplitude of the modulating signal, AM. This catches so many students off guard because they just assume FM parameters only relate to frequencies. Don't be one of them.
Moving right along to phase modulation, or PM. Here, the phase varies linearly. Your phase sensitivity constant is Kp, measured in radians per volt. To find your phase deviation, you just multiply Kp by the message amplitude. But here is the trap.
And it's a good one. If they ask for frequency deviation in a PM system, you must multiply your phase deviation by your modulating frequency. Read the variables carefully. Ensure you don't mix up the FM frequency deviation constant with the PM phase sensitivity constant. They love testing that distinction.
We are making great time. Let's hit pulse modulation techniques next. This area is highly conceptual.
Examiners love testing your ability to classify these systems. Analog pulse modulation includes PAM, PWM, and PPM. Digital pulse modulation includes PCM, DPCM, and delta modulation. The ultimate trip up here, it's seeing the word pulse in pulse amplitude modulation and automatically assuming it's digital. PAM is strictly analog, folks, because the pulse parameters vary continuously. Do not fall for that trick.
Let's look a bit closer at PAM. While the amplitude varies, the transmission bandwidth depends entirely on the pulse width, not just the baseband signal. Even though PAM is simple and forms the literal foundation for digital PCM, assuming its transmission bandwidth simply equals the baseband bandwidth is a very sneaky exam trap that'll cost you 1/4 of a mark before you even realize what happened.
All right, it is time to put all of this to the test with our final section, high-yield exam traps.
We're going to run through some actual numerical and conceptual tricks pulled straight from the syllabus material. Read this question carefully. In digital communication, redundancy is added to what? Think about it for a second. Lock in your answer.
The answer is to detect and correct errors, often referred to as forward error correction. The big trap here is thinking redundancy improves speed or somehow saves space. It definitely doesn't. Adding redundancy is essentially a protective tax you pay on your bandwidth just to ensure data integrity.
Let's see how this builds into a math problem. Say you're given a carrier signal C of t equals 4 times the cosine of 2 pi times 1000 t, and you're asked for the average transmitted power. Step 1, spot your amplitude, AC, which is 4. Step 2, and this is critical, do not just square the amplitude. That is the trap. You have to divide the amplitude by the square root of 2 to get the RMS value before squaring it. So 4 over root 2, all squared, equals 16 divided by 2, giving you 8 watts of true carrier power.
Well, we've covered the exact blueprint, the signal foundations, the dense formulas, and those high-yield traps. But I want to leave you with one final thought to ponder as you continue your last-minute prep. If standard AM efficiency is permanently capped at a measly 33.3%, where exactly does the remaining 66.7% of your transmission power actually go? And more importantly, how do modern telecom engineers fix that massive inefficiency? I highly urge you to review your single sideband concepts on your own before test day. Stay focused, trust your preparation, and go ace that exam.